We will discuss the technology for understanding and quantifying geomechanical changes in reservoirs. Tom Davis is professor at Colorado School of Mines. He's usually here with us in Dubrovnik, so we hope that in the next years situation will be different. But of course, feel free to ask any question, and that's it. I think that we can start.
Thank you very much, Dobar dan. I want to present to you technology for understanding and quantifying geomechanical changes in reservoirs. This is something that I've been working on for years, and part of it is affiliated with my association with the Colorado School of Mines and the Reservoir Characterization project that I created. We've been doing time-lapse multi-component seismic surveys since 1995. And over the years, I've presented to the PESS some of our studies, especially pertaining to carbon capture and storage, and the monitoring of these storage projects and enhanced well recovery projects. Today, though, I want to share with you some of the investigations that we've conducted, mainly pertaining to hydraulic fracturing in unconventional reservoirs. And the premise of doing this work is that we're dealing with geomechanical changes in the reservoir when you're injecting fluids. So geomechanics is the study of stress in the subsurface, and time-lapse seismic is a methodology for observing and understanding these changes and potentially quantifying these changes in the subsurface. Time-lapse seismic, or what we call 4D, is akin to medical imaging. That is, you take an image, and then sometime later you take another image and you difference those images to see what changes. And in this case, we're looking for changes in the stress field to enable us to understand better how we're completing wells, especially in these unconventional reservoirs. So in this case, we have a massive injection of fluid to create the hydraulic fractures in the first place. And what it does is create a pressure variation in proximity to the well, and that changes the stress field in that proximity. And that also changes velocities, not only, as we often think about it, right near the well, but sometimes above and below. So in this case, these geomechanical changes are volumetric in that they occur not just locally, but they're transmitted by stresses into the subsurface. And by changing in the velocity, we can measure these changes with time-lapse seismic by various means. One is to investigate time shifts, and I'll talk more about these time shifts as I go on. But there are other ways too that we can look at changes in impedance, which is the product of velocity and density, which also changes amplitude of our data. Now, I've been involved with what we call permanent reservoir monitoring projects all over the world. And most of my studies at the Colorado School of Mines have been conducted in North America, of course, because of proximity. But I've been on the board of Geospace Technologies since they went public in 1997. And also in 1997 was my first trip to Dubrovnik, my first time to come and present at the PESS. These projects that were undertaken by Geospace were largely offshore in large or giant fields in the North Sea, offshore Brazil, and various other places. So Geospace conducted permanent reservoir monitoring projects, both onshore and offshore, and we worked with them closely with our onshore projects as well. So what are permanent reservoir monitoring projects? Well, in this case, what we do is install an array of receivers that will measure ground motion, and we leave that array in the subsurface or on top of the surface, as the case may be, for some period of time. And then we continuously monitor the subsurface in terms of recording these data. Now, sometimes you don't have to record all the time. Other times you want to record all the time. And so what we need are, I guess we'll say, facilities that will allow for the acquisition and processing and analysis of seismic data over long periods of time. And where multi-component seismic comes in, it's just a fancy word for full waveform seismic. We aren't just measuring the compressional wave or P wave as we often do when we acquire seismic data. We're acquiring also what we call shear waves. These are waves that have horizontal particle motion. And these waves are especially sensitive to stress in the subsurface. In fact, there's almost a linear relationship between shear wave velocities, variations, and stress. So this gives us a good hope to quantifying some of these measurements. And whereas compressional waves, generally we find that they're nonlinear in relationship with stress. And often they may not provide the entire information we need, but they're easier to acquire, and a lot of people do that. Now, for a long time, we've been working on measuring or observing anisotropy. And anisotropy is just the change in velocity with direction. So one of the advantages of shear waves is that if you inject them into the subsurface, they polarize into, and they cross an anisotropic body. Perhaps it's a fractured body. For example, you get two waves that come out, which we call an S1 fast wave and an S2 slow wave. Now the S1 propagates parallel to the major axis of anisotropy, or the fast direction. S2 is perpendicular and it propagates in that direction, perpendicular to the fast. So it allows you to take a body of subsurface rock and basically treat it like a deck of cards, where you're basically looking at rigidity in one direction and then twisting this in a different direction to measure these changes in velocity. And we translate that into a velocity anisotropy measurement. And it's very sensitive to stress. So in our case, what we conducted along with Talisman Energy, based in Calgary, which is now part of Repsol, 3 seismic surveys to monitor 2 hydraulic stimulations in a field in northwest Alberta. We were intentionally evaluating shear wave, what we call splitting, that is the observation of the shear wave into these fast and slow components, and then measuring time shifts, especially in the overburden, where there was zones of high reflectivity above the main reservoir. But the main reservoir itself was pretty low reflectivity. So we've got horizontal wells that were drilled back in 2008, and they were hydraulically stimulated with the same, basically, process in each of the wells. And what we observe is that by pressurizing the wells, we could observe changes in velocity and shear wave splitting above the main reservoir. And so this is the survey design. Again, there are a number of horizontal wells, but we were mainly targeting 2 that were being completed during the course of our survey. We've installed 135 permanently installed seismometers in cased holes, and it was just PVC casing. So we drilled the holes down to 15 meter, put PVC pipe in the holes, and then put down these 3-component or multi-component receivers that can measure vertical displacement as well as 2 directions of horizontal displacement. And then we used dynamite sources to propagate energy into these arrays on a very short time basis. So in this case, we needed a large number of source points to give us a maximum signal to noise ratio to enhance the signal content. The bin size, since this is a 3D survey, in other words, the shot holes are laid out over a grid, the sources are over a grid. So we're basically sampling 100 meter bin size in the subsurface at depth. So these are our source lines across the area, and this is a fairly small area. And these are our receiver holes that were dug into the subsurface. And the location of the survey is in northwest Alberta, in the vicinity of a field called Pouce Capet. And this is a reservoir called the Montney. And this Montney reservoir is a huge mainly gas reservoir. On the proximity landward towards Alberta, though, it becomes more gas condensate and even some places oil. But we were mainly focused on gas in 2008 because at that particular time, gas prices were quite high. The interval, as I've already mentioned, is a fairly low reflectivity interval. And in this case, I'm showing you what's called PESS. That's a propagation of a compressional wave going down at some angle of incidence, not just vertical, but it hits the top and bottom of the reservoir and transmits a shear wave that comes back up almost vertical into that array. And we observed that in this case, there was splitting because there was a time variance between the S1 and the S2 shear waves. So you can introduce shear waves even with compressional wave seismic data at offsets to the normal incidence. And these travel times and amplitudes are very sensitive to the properties of the reservoir, since this is a naturally fractured reservoir, but we're on top of that hydraulically fracturing the reservoir. So in this case, it requires extensive processing to enable the separation of these shear waves. And then after you've done that, you want to make sure that since we're looking for very small changes, that the processing is done accurately. And one of the limitations of this technology over the years is that very few seismic processors are capable of processing data like this. But in Canada, they do a lot of this because they use a lot of this technology, especially in the heavy oil in the northeastern part of Alberta, in injecting steam. So they do a lot of steam flood monitorings with this technology. But we are mainly interested in whether we could observe these changes, monitor them, and try to quantify some of these changes. So this was done in December of 2008. And there was a baseline, a first survey, if you want to call it that, conducted December 8th through the 10th. It took a couple of days to acquire the seismic data. Then one of the wells, which is called the 2 of 7 well here, was fracked, hydraulically fractured on December 12th. On December 13th and 14th, we did another survey, which we will call a Monitor 1 survey. And then the 7 of 7 well was fracked on December 17th, and we did a second survey December 18th through 19th. So again, all 3 surveys spanned a time interval a little bit more than 10 days. I should point out that there are frac stages in these wells. In this case, there were 5 frac stages in each of the wells. And again, a similar quantity of fluid was injected in each one of these frac stages. It doesn't mean that they're all the same, however, because observing in the subsurface, there are areas of natural fractures that you're injecting near or within. So not all these wells perform the same, and we're trying to understand why. So back to the seismic data. How do we interpret these time shifts? Well, if you got one survey and you're looking at a reflector that's from on top of the reservoir or on the bottom of the reservoir or even within the reservoir, you can compare it to the next survey, the monitor survey, and see whether there is a time difference. So it takes time to go from the surface down to the reservoir and back up to the surface to these geophones. And these time shifts are relatively small, and we were measuring changes in the order of microseconds. In this case, I'll show you a graph that shows basically a change over -5 milliseconds to +5 milliseconds. So if we got a change from the original to the next survey that's shifted upwards in time, or a shorter time interval, or smaller time interval, we will call that an increase in velocity. So what that means is that pressurizing the well lifts up the overburden, or compacts it, I should say, and increases the velocity, interval velocity above the reservoir. And we measure that by these time shifts. In this case, we're measuring an increase in velocity or a positive time shift. And of course, if it goes the other way, in this case, it'll be a decrease in velocity or a negative time shift. So what generally, and just to give you an idea here, what we think is going on in the subsurface is that if we have a proximity to natural fractures, we're going to open up those fractures and decrease the velocity because the rigidity of that medium drops. And the shear waves are very sensitive to rigidity. In fact, their velocity is controlled by the square root of rigidity over density. So we don't think we're changing the density a whole lot, but we are changing substantially the reservoir of rigidity. So if we're injecting near or into a natural fracture system, we will observe decreases in velocity. If we're injecting in areas that aren't naturally fractured and we're pressurizing that reservoir interval and compacting the overburden, we will see a positive time shift or an increase in velocity above the reservoir. So is this theoretically achievable? Yes. We did some modeling. Yes. Do we observe these changes in reality? And the answer, we think, is yes. On the compressional wave data, or what we call PP, that is P going down, P coming back, that is the vertical ground motion that's sensed at the surface by the receiver. In this case, these changes over a scale from -5 milliseconds to +5 milliseconds are shown, but they're very small. They're probably on the order of 1 or 2 milliseconds. Are they observable? Yes, but if you have any noise at all, you're gonna probably not see these very definitively. Whereas on the shear wave data, what we call PESS, because we have P waves going down at some angle of incidence, converting to shear and traveling back up as shear waves, these are more sensitive to stress, as I've already alluded to. So the red changes here are positive time shifts. And these time shifts occur, as we see, largely above the reservoir, but sometimes even below the reservoir or within the reservoir. And the blue areas are areas in which we observe decreases in velocities or negative time shifts. And these are measurable as approaching 5 milliseconds. So they're twice the, I guess we'll say, value of the P wave changes that we observed and are more observable. So on the P wave data, if we were to do a slice through the reservoir interval or above, as we're doing right here, what we see are small changes, again, in that order of plus or minus 2 milliseconds. And in this case, one of the things we observed is that these changes are dominantly between the two wells. And we still have kind of a problem understanding why that is, but when we're fracking these wells so close in time together, it's logical that you'll have stress transmission away from the wells laterally as well as vertically. So it may help us, this technology may help us with understanding the drainage of these horizontal wells and over time. In this case, the PS1 data, this is traveling, the shear wave is traveling parallel to the main fracture trends, which are to the northeast here. Just to the west of this, we have a thrust belt, and the transmission of stress, horizontal stress, is in this northeast direction. So in this case, we see the baseline versus monitor 1. That's when we were fracking the 2 of 7 well. We can see that there are observed changes, higher velocities or positive time shifts in certain locations near the wells, well, near the 2 of 7 well. And again, there are changes around this area. So one of the questions is what's real and what isn't, especially if we're dealing with the same kind of magnitudes of change. Are we truly transmitting stresses over these large distances or not? And that question still perhaps needs to be addressed. In this case, baseline to monitor 2 survey, this is when we're fracking the 7 of 7 well to the northeast. We see less observation of change. So is this real or is it not? Is there production information that we can include to understand this more, et cetera, et cetera. But the real shear wave that is most sensitive is actually transmitted across these natural fractures and for that matter, hydraulic fractures, because the hydraulic fractures go in the direction of the maximum horizontal stress. That is, they're going to be transmitted towards the northeast, paralleling the natural fracture network in this reservoir. And the S2 shear wave propagates orthogonally or perpendicular to the main fracture trends. So in this case, we think this shear wave, what we call PS2, is more sensitive to the stress. So as we open up these fractures aligned in the northeast direction, the orthogonal shear wave, which is transmitted orthogonally to that direction, will sense that opening. And in this case, we see the baseline to monitor 1, the 2 of 7 well, an area, especially in the area near the where the well went into the reservoir, we see a higher velocity or positive time shifts. Whereas at the end of that, or the toe of that well, we see negative time shifts. So what is that telling us? Well, we found that towards the toe of this well, there's a fracture zone. So these dashed lines are areas in which we interpret some northeast trending natural fracture zones. What we're basically doing in that well is opening up those natural fractures. And that can be good or bad with the stimulation of these horizontal wells, as I'll show you. And in the 7 of 7 well, when we look at the baseline versus monitor 2, we see positive time shifts kind of in the center of that well. And we see negative time shifts where the well went more into the reservoir. Again, these wells were drilled in a direction perpendicular to the natural fracture system. And the toe was at in this case, the southeast end of the wells. So what does additional data show us? Well, this is the microseismic that was recorded during the fracturing of these wells. Most of the microseismic was recorded from a downhole array in proximity from a vertical well in proximity to these wells. But there was also a horizontal array in one of the wells as well. And what we're seeing here is that there's areas, I guess we'll just say these dots indicate higher levels of seismicity that were induced during the fractures. And there are 5 frac stages in each of these wells. So each of those stages is monitored here. And we see this increase in seismicity, especially in the 7 of 7 well. Now, people would logically say that if you have more seismicity induced, you're going to have a better well, because they translate that into longer frac lengths, which generally are adopted as having greater, I guess we'll say, communication with the reservoir. But as I'll show you, that doesn't necessarily pertain here. The best well is actually the 2 of 7 well, where the microseismicity is more localized. And this has surprised a lot of folks in our industry. So in this case, what we believe occurs are areas in which we're opening up natural fractures, and these natural fractures sometimes will transmit fluids away from the wells to the point that we don't have as effective recovery. So just to further point this out, this 707 well, most of the flow in the well, since they did a production survey in the well, most of the production from that well, over 40%, comes from just one of the frac stages. And in this case, this is also the area where we have positive time shifts, which tells us that the frac is not going outside of the reservoir. In other words, we have containment of that hydraulic fracture. And in the 2 of 7 well, the same thing occurs. We have these areas where we have effective containment, but we also have some areas near the toe of that well in which we don't. And this is seen from the arrays, microseismic arrays that we had. We have areas, especially in that 7 of 7 well, in the middle part of that well, the 3rd frac stage, where we had containment within this Montney interval that we were fracking. Whereas other areas, we were fracking right out of zone. And that was detrimental to the performance of the well. And just to relate this back, again, we see it in terms of these time shifts, not just with the microseismic. So again, these are long reach horizontal wells. In some cases, we have wells that are landed in the C zone of the Montney. That's an interval below. Another well, the 7 of 7, was located in the Montney D. So they're not necessarily in the same zone. And I want to clarify that. It would be nice if they were in the same zone, but they aren't. They're separated by a very short distance, though, as looking at this scale on the left side. And again, let's look at the production data. In 2 of 7 well, we had all 5 frac stages were producing at roughly the same amount, except one of those frac stages, especially towards the end of the well or toe of the well, produced less. Whereas in the 7 of 7 well, the one to the northeast, we have over 40% of our flow come from that central frac stage, and not so much in the others. And this is borne out in terms of longer term production histories from the wells. Again, the 2 of 7 well compared to the 7 of 7 well is a better producer. In this case, I just want to indicate what the hydraulic fracture parameters were. We're dealing with 5 stages, 100 tons per stage of fluid induced in each of those stages. And this is even, well, I guess another way of depicting this well performance, a better way, in that we're looking at accumulated gas over a period of time after the wells were stimulated and then flowed back. And in this case, we're looking at the Montney C production from the 2 of 7 well exceeding that of the 7 of 7 well, which was completed in the Montney D. And so just to wrap things up here and give you some time for interaction and questions, the analysis of these time shifts and the overburden we think is an indication of stimulation performance. And we've actually done this work in other locations now to indicate that this is very real in terms of our ability to use this technology in a sense that can have value to our community. The multi-component seismic is a very valuable tool, and especially with the full waveform recording as we did with shear wave data as well as compressional wave data. In fact, we use what we call 9-component data, which allows us to record pure shear data as well, where we induce horizontal polarized waves from shear wave vibrators into the subsurface, and not just rely on compressional wave data for transmission of these shear waves. Time-lapse seismic data allows us to monitor these hydraulic fractures. So we have to look at going forward here, and going forward, the seismic tool is a very useful tool for observing geomechanical changes as we've observed. And the best way to do that is with permanent reservoir monitoring setups. Now, that means that you have to be able to go into areas and install arrays of receivers and leave them for some period of time. And in some cases, especially in active oil field or gas field environments, sometimes that's really not too feasible. So what can you do? Well, you can install arrays within wells, perhaps wells that you haven't been using. So you can put in vertical arrays to observe these changes, and then have less footprint on the surface, and that works. Or right now, a lot of the technology is changing towards fiber optic monitoring, where you can install fiber optic cables in wells or even in the subsurface if you can achieve that. So there's different mechanisms. And importantly, the processing of the data has been accelerated to the point of creating value here, in the sense that we want to observe these time changes, especially in real time. And that's achievable. And we do that now with very fast processing technologies, and sometimes using artificial intelligence and networks. And so the technology is rapidly advancing to make use of this, these observations. And the microseismic is a tool of value, but by combining it with these other technologies, we can go beyond just observing these so-called dots in a box. That is just observing where the microseismicity occurs, and helping us to understand that sometimes where we get high levels of microseismicity isn't always where we want to be. That is, that doesn't always dominate where flow is in the subsurface. And from an engineering point of view, we need to look at trends of performance. How do we quantify these observations, bring it back to stress magnitudes, and bring that back into the idea that getting a bigger hammer, as we have within hydraulic fracturing, isn't always the best. So sometimes low stress changes or loads can have better performance results than the high stress loads of injected fluids in these wells. And so we need to understand how do we make these completions more effective. And sometimes, again, as I said, a bigger hammer is not always the best tool. So we have to look at integration here of disciplines and technologies to be able to enhance our recovery from these horizontal wells and unconventional reservoirs. and we can do so. And it's one of the reasons why geomechanics, as you're understanding during this week, is going to be critical to the future of our business. And whether that business be oil and gas related or geothermal related or whatever, but wherever we're injecting or withdrawing fluids, we create geomechanical changes in the subsurface. And these are observable with seismic and can be quantified and then used. So in summary, I call this high definition reservoir characterization or dynamic reservoir characterization. So in this case, we're looking at dynamic changes in the reservoir, sometimes over very short spatial time intervals. And to record and observe these, we need permanent reservoir monitoring to do so. And the industry is moving in that direction and moving very quickly to do this. Generally, it's been done in offshore reservoirs and very high volume wells in places like the North Sea or in offshore Brazil or the Gulf of Mexico. But we can scale this down to observing these changes even within unconventional reservoirs or shale reservoirs, as we're doing in North America and other places. And to do this effectively, we have to involve ourselves in the integration of technologies and disciplines to pull this off. And in doing so, I think we can advance our value to society. And we can also go back and refrac a lot of wells that have already been fracked and not been fracked successfully. So one of the things I want to leave you with here is that we're not done. In other words, a lot of people, especially in unconventional reservoirs, are thinking that it's one and done. In other words, one drilling, one completion, stages, perhaps in these wells, and then you move on or just wait. Well, we can go back and do a better job than what we've done in the past.